Why the binomial becomes normal. When does a staircase of binomial probabilities look like a bell curve? Binomial to normal convergence shows how a standardized binomial count becomes approximately normal. As the number of independent Bernoulli trials grows, while both expected successes n times p and expected failures n times 1 minus p are sufficiently large, the finite distribution remains discrete. The normal curve is an approximation, not a replacement of its mechanism. Use the visualizer to inspect center, spread, skew, and overlap. Then check the exact probability relevant to your decision. For large enough n with p away from the boundaries, z equals x minus n times p divided by the square root of n times p times 1 minus p and converges to a standard normal distribution. On the original count scale, this motivates a normal model with mean n times p and standard deviation equal to the square root of n times p times 1 minus p. A continuity correction adjusts a discrete boundary by 1/2 when a normal area approximates a binomial sum. For example, px less than or equal to k is approximated by a normal probability up to k plus 0.5. The visualization illustrates shapes, but does not automatically present a corrected probability calculation. Convergence in distribution concerns cumulative probabilities at continuity points of the limit. It does not say individual binomial observations become continuous, that exact masses, equal density heights, or that all tail errors vanish at the same rate. Compare two binomial sequences. First set p equals 0.5 and increase n from 10 to 100. Then set p equals 0.1 and repeat. The goal is to observe why the smaller of n times p and n times 1 minus p controls the slow side of the approximation. At n equals 10p equals 0.5, expected successes and failures are both 5. The shape is symmetric but visibly discrete, so a normal approximation may be only rough for narrow or tail events. At n equals 100p equals 0.5, both expectations are 50. The mass is concentrated across many adjacent counts, and the matched normal curve follows the center closely. At n equals 10p equals 0.1. Expected successes equal 1, and the distribution is strongly right-skewed. Even at n equals 100p equals 0.1, the smaller expectation is 10. The match improves, but tail accuracy still deserves an exact check. The experiment demonstrates that large n is relative to p and to the probability being approximated. It supports using both expected successes and expected failures as a screening rule, applying continuity correction, and preferring exact binomial calculations when they are readily available. Try it free at distryscope.com.